All right, so let's take a look at the next example, 2.29. This is regarding the scalar projection of velocity. So we're told that a container ship is leaving port 15 degrees north of east. We know that the engine generates a speed of 20 knots along that path based on the figure that we have here. And in addition, the ocean current moves the ship northeast at a speed of 2 knots. So considering both the engine and the current, how fast is the ship moving in the direction of the 15 degrees north of east? All right, so this is example 2.29. Scalar projection of velocity. So what do we know? We know a ship leaves traveling 15 degrees north of east with a engine generating a speed of 20 knots. All right. We know that the ocean current is moving the ship northeast at a speed of 2 knots. We're interested in finding how fast the ship is moving in the direction of 15 degrees north of east. Let me go ahead and take the image that they've provided to us. All right. So we have our vector v. This is our velocity vector that's representing the actual movement of our ship. So let's go ahead and sort of translate this information here. We don't have the exact vector. We could certainly figure it out using the component rules that we discussed previously, right? That cosine sine business. But we're only interested in speed, right? So this is the magnitude. So the speed is going to be the magnitude. Yes? We're not actually interested in finding the exact vectors. We're just interested in finding their magnitudes. So we know that our velocity in this north of east follows the path of our vector v here. This tells us that the magnitude of our vector v is equal to 20. Similarly, with our w vector, that's what they call their current, right? So this is northeast at a speed of 2 knots. So this is telling us that the magnitude of w is equal to 2. And we know that this angle is equal to 45 degrees. All right, so what we want here then is the scalar projection. So to determine how the current is affecting our velocity, in that particular direction, we need to calculate the scalar projection of W onto V. Right, we're just interested in how much of that 2 knots is actually being applied to the velocity in this direction. So let's scroll back up and see what that formula for scalar projection was. Let's see. So that's our resolution. Here we go. So the scalar projection of one vector onto another is denoted by this comp sub u of v, which is the absolute value of their dot product divided by the magnitude of the vector that we are interested in to the projection onto. Right, so our subscript tells us exactly what our denominator is going to be. So scrolling back to our work, taking it a second to kind of load up. So the component of our vector W onto V is equal to the absolute value of their dot product divided by the magnitude of V. So this begs the question, how do we actually calculate the magnitude of the dot product? We don't know what the vectors are. Well, fortunately, we had another very handy rule that said that the magnitude of the dot product is the product of the magnitudes times cosine of the angle between them, right? So everything's kind of coming back to assist us here. All right, so the magnitude of W is, well, let's go ahead and write it out. We have this simplifying term, so that's very nice. The magnitude of W we said was 2 times cosine of, no, we are only interested in our angle between the two. So, since we're going from the 15 degrees to the 45 degrees, our angle between the two vectors is 30 degrees, right? So let's just sort of make that note here, which is that 30 degrees is because we have the 45 minus the 15, which is the angle between B and W. All right, and this becomes then rounded to 2 decimal places. Let me go ahead and pull up my calculator once more. Cosine of 30, I believe, is not a nice one. Let's see. We want to make sure that we are converting. Okay. So our final answer, round 2 decimal places, I think as it suggested, is 1.73. Right? So this is, just recall, representing just the effect of the current. So the ship is actually moving the 20 knots that we had originally, plus this expression here. So 20 plus the 1.73, which is going to give us a final answer of 21.73. Let's check our answer. Okay, so we know that the magnitude of V is 20. We're calculating the component of W onto V, doing that translation from our dot product into our product of magnitudes times cosine of the angle between us. There we have our cosine of 30, beautiful, 1.73 knots. So a total answer of the 21.73. All right, so let's take a look at the checkpoint problem. We're going to repeat the previous example, but this time we're going to assume the ocean current is moving southeast instead of northeast. So this sounds like it might slow us down a little bit. Let's see. Go ahead and pause here and work on that on your own.